Okay, good day. This is AP Calculus. I am Mr. McCulley, and this is the presentation for Section 3.2, Rolles Theorem and the Mean Value Theorem. And let's get right to it. So, today we are talking about Rolles Theorem and the Mean Value Theorem. These are two theorems that are quite often applied or asked to be applied during one of the extended response questions on the AP Calc test. Now, we are not going to use these two theorems very on explicitly where we're saying, okay, we're using the mean value theorem or we're using Rolle's theorem, but we certainly are going to use the concepts and some of the things that go on behind the scenes or some of the concepts that go with these two theorems. So let's get right at them. And so Rolle's theorem's definition is on page 172, and the basics are this. First, and hint, hint, you might see that I have that first basic both underlined and bold-faced. You might see that somewhere down the road. But first off, for both of these, the function must be continuous over a closed interval. The moment that there's a discontinuity of any kind in the interval, this theorem no longer applies. So if the function is continuous over a closed interval and the two endpoints of the function on the closed interval are equal, then there must be a place in the interval where the first derivative is equal to 0. So let's pick an interval. Let's say our interval is going to be from -2 to +3. There's our interval. And our function from -2, it starts at 1, and then it kind of comes up here, and then eventually when we get down to 3, it stops right there. And so over this closed interval, we also see that f of -2 is equal to f of 3. Now, since it is both continuous, there's no obvious discontinuities, and the endpoints of the closed interval are equal, there must be some value between 2 and 3 where we have the first derivative equal to 0. And obviously, at this point right here, I could draw in a horizontal tangent line right there. And so there is how we can see for sure that Rolle's theorem applies. Now, the mean value theorem is a more general version of Rolle's theorem, and basically what it says, again, it must be continuous over a closed interval, but basically it says on some closed intervals, let's have a new or a different closed interval. Let's say we're going to go from, let's say, -4 to 1, and we have some function that looks like this. Let's see, here's -4. And then at 1, it's right here. Say like that. All right. Now, what the mean value theorem says is that there must be a point where the slope of the tangent line is the same as the slope of the line that connects the two endpoints. So if I come in here, and this is probably going to be too big, so let's make it a little smaller. Let's make it a lot smaller. If I come in here and I make a secant line, and that might be too small for people to see, so I'll make it just a skosh thicker once I get it where I want it. Right there. Properties. That's not what I want. I want, let's go back to here. Let's select these line properties. Page recording, graph settings. Huh. Oh well. We will just, you know what? We'll just redo it. And just draw another one in. I'll get rid of this. I'll just draw another line a little thicker. Oh, that one is thicker. Okay, let's undo it. There we go. Oh, I know why. That's why. Now I should be able to get it. There we go. Haha. A little thicker. That's good. Okay. That works. Okay. So basically what it says is that if I draw this secant line in there, then there has to be at least one other place where along this curve, the first derivative is the same value as the slope of this secant line. And it wouldn't be too big of a stretch for us to see that if we're talking about, there might even be two in this one. Certainly up here we could have a tangent line that's parallel, like right there. So at this value, we'll call it C. And let's see, maybe if we do a clone here, maybe right there, there's also another one. So you can have more than one. All this really says is that there has to be at least one. And so we'll call that E just for fun. All right, so those are the basics. So looking at this, determine if Rolles theorem applies and find the value on the open interval where the derivative of the function equals 0. So I look at this thing here, and here's my closed interval. It's 1 to 4. And so if I find f of 1, then 1 squared is 1 minus 5 times 1, or yeah, 5 times 1 would be negative 4, plus 4 is 0. Okay. F of 4, well, let's see here. 4 squared is 8. No, 4 squared is 16. Come on, Macaulay. 4 squared is 16. 4 times negative 5 is negative 20, which would be negative 4 plus 4 is also 0. So the endpoints are equal. Since this thing is a parabola, it has to be continuous on that closed interval. So Rolles theorem does apply. There's two L's and apostrophe and Rolles. There we go. Rolles, Theor, period, applies because f of x is continuous on the closed interval and the value of the endpoints are equal. So I look at this thing here, and I have to find the value on the open interval where the function is equal to 0. So we know how to do that. F prime of x is going to be 2x minus 5. And so certainly if I set that equal to 0, I will find all of the places where this function f has a tangent line whose slope is 0. So I add 5 to both sides. 2x equals to 5, and then x would be equal to 5 over 2. And certainly 5 over 2 is 2.5, which is between these two. So there's the second part. And we are done. Let's look at this next one. It says, determine if Rolles theorem applies and find the value on the open interval where the derivative of the function is equal to 0. And so I look at this particular problem here, and I don't have an open interval, and I should have an open interval. So let's just make it from -2 to +2. And here's the problem. I certainly see that at x equal to 0, there is a non-removable discontinuity. I don't think I spelled that right. Discontinuity. Maybe that's an I don't know. It's escaping me now. Sorry, guys. Anyway, there's a non-removable discontinuity, thus Rolles theorem does not apply. Okay, so let's try one for the mean value theorem. The mean value theorem is a little bit tougher. And so we look at this particular function here, and certainly this function is continuous over 0 to 2. And so we want to find a place over this interval where the value of the derivative is equal to the slope of the secant line. Well, before I can do that, I got to find the slope of the secant line. And remember, m equal to y2 minus y1 over x2 minus x1. Well, in this particular case, it's going to be f of 2 minus f of 0 over, no f's on that one, over 2 minus 0, which in this case, if I plug in 2 to the fourth is 16, and 2 times, let's see here, 2 times negative, or 8 is negative 16, so I get 0 minus 0. Did I do that right? I need to check that. I need to check my work. I'm feeling confident. 2 raised to the fourth, and then minus 8 times 2 is 0. And then when I plug in 0, I'll get 0. So this is another instance where of the I get 2 minus 0. So this would also work for Rolles theorem, because the endpoints end up being the same here and here, and it's continuous. And so I need to find that first derivative. F prime of x is going to be 4x to the third minus 8. And we need to know where that thing is equal to 0. So I'll come over here, 4x to the third minus 8 equal to 0. And so we bring the 8 over to that side, get x to the third is equal to, or 4x to the third is equal to 8. And then x to the third is equal to 2. So x equals the 2 to the 1/3 power. And that is definitely between there. 2 to the 1/3 is, let's see, grab my calculator here. 2 raised to the 1/3 power is 1.295. 1.25, or actually 260 when I round it. So certainly that is the point. So yes, the mean value theorem applies, and we get an x of 2 to the 2/3. All right, example 170, page 177, number 62. At 9:15 a.m., a sports car traveling 35 miles per hour is traveling at 35 miles an hour. 2 minutes later, the car is traveling at 85 miles per hour. Prove that exactly some time during this 2-minute interval, the car's acceleration is exactly 1,500 miles per hour squared. Okay, well, let's talk about that. First off, 2 minutes. There are, let's see here, 60 minutes in an hour. So that'll be in 1/30th of an hour. In 1/30th of an hour, this is going to be my change in time. And so acceleration, you'll remember, is the change in velocity over the change, I'm getting too big on my D's. It's going to be the change in velocity over the, I almost did it again, change in time. So in this particular instance, I got, let's see here, 85 minus 35 all over 1/30th. And so I get 50 over 1/30th, which would be 50 times 30, which is 1,500 miles per hour squared. Okay, so this thing is the average acceleration. All right, and so basically, when it accelerates from 35 miles an hour to 85 miles an hour, that might not be a constant acceleration. They may hit the gas, they may take off the gas, they may hit the gas, they may take off the gas. But over that time, the average acceleration is 1,500 miles per hour squared. Thus, let's quote thus by the mean value theorem, there must be some time between the 2-minute interval where the acceleration is exactly 1,500 miles per hour squared. Well, that's all I got there today there, folks. So we are to the Star Wars fun fact of the day. And here, today's fun fact is this actor here, Dennis Lawson from Star Wars Episode 4, A New Hope. His name is Dennis Lawson, and he played Wedge Antilles. He was the one fighter pilot that got away from the Death Star trench run. He is the uncle. This guy is the uncle of a Ewan McGregor who played Obi-Wan Kenobi in episode 1 through 3. And so we have a nice familial connection. Oh, that's all I got today, folks. You have a great day, and I will see you in class.